So check B. B spans V. Okay, right, so consider a polynomial Pt, which is equal to alpha 0, alpha 1t plus alpha 2t squared plus theta plus alpha n Tn in P. But when we write a polynomial in P in this way, so it is clear that Pt is a linear combination of 1 t squared up to Tn, okay, which are vectors in the set B. Okay, in the set B. Alright, so P contained in the span of B okay. Alright, so and then P is equal to the span of B. Questions? So we finished the first part to show B spans V. Any questions? Okay, no question. Good. B is linearly independent. Okay. All right, so consider a linear relation on B. Okay. Okay, so a linear relation on B can be written as say beta 0 0. Okay. So any linear relation on B, because a linear relation is just that a linear combination of vectors in B. Okay, so you collect finite of them from this collection, and let it equal to the 0 polynomial. So this one, this 0 means the 0 polynomial. Okay? Okay, so you may argue that why you put consecutive monomial together. For example, maybe you say, I just want to pick up t squared and the t fourth power and the t sixth power, only 3 from this collection. Why you put all of the polynomial up to 6? Well, you can just put the 0 coefficient there, right? you get the same linear combination. So if you want to put, say, right? You want to say that this is a linear relation involving t squared, t4th power, and t6th power. I want to consider such a linear relation. That's fine, because, well, this is going to equal to 0 plus 0 t plus right? You just put 0 to all the other monomials there. Okay, so this is, again, is a linear relation. Okay, so without loss of generality, we just consider this kind of linear relation. Okay, so that this is the zero polynomial. All right. Now, by definition, of the zero polynomial, we have beta all the coefficients to be 0. This is what we mean zero polynomial. Okay, so that so B is linearly independent. So we conclusion. P. Okay. All right. So the vector space of all polynomials has a basis. All right. This basis is an infinite set of vectors. Questions? Okay. No questions. Good. The second example, in ordinary differential equations, you learn a special type of polynomial called the Legendre polynomials. So the first 4 is a sequence of polynomials, very special types of polynomials. But I just list the first 4 Legendre polynomial. Okay, so the first Legendre polynomial is just the constant polynomial 1, and the second one, P1, is t. Right. So 0 is it denotes the degree of the Legendre polynomial. So the Legendre polynomial degree 0 is 1. The Legendre polynomial of degree 1 is t. But the Legendre polynomial of degree 2 would be 1/2 of 3t squared minus 1. Okay, and the Legendre polynomial of degree 3 is 1/2 of 5t cubic minus 3t. Okay, so these 4 Legendre polynomials will a basis for P3. For P3, big P, right? So P3 is the vector space of all polynomials of degree less than or equal to 3. Okay, and we also know P3 is a vector space in chapter 2. Okay. Right. So we have to check two things. So we let B equal to P0T, P1T, P2T, P3T. This is set spans P3. Okay. So we first check that. Right, so let Pt equal to alpha 0, alpha 1t, alpha 2t square, alpha 3t cubic. Right, so we consider a vector in P3. Okay? And we try to represent this polynomial as a linear combination of the Legendre polynomials. Okay, so we want to find so this polynomial is given, but we want to find the coefficient of the linear combination x0, x1, x2, and x3. Okay, so we just substitute this Legendre polynomial into here. Okay, so we find that we have x0 minus half x2. This is the constant coefficient x1 minus 3/4 multiply x3 t plus okay, so now this is to combine like terms together. All right, this is the common practice when we deal with polynomials, right? So we just combine like terms. After you plug in this Legendre polynomial into here, you get all these things here. Okay, and so these two polynomials are identical, so that we have alpha 0 is equal to x0 minus 1/2 of the x2. We have alpha 1 equal to x1 minus 3, and alpha 2 equal to 3 half of x2 and alpha 3 and 5 half of x3. Okay. But the unknown are xi's, so that's we will have x0 can be expressed by alpha 0 plus 1/3 of alpha 2, and the x1 equal to alpha 1 plus 5, so it's 3/5 of the alpha 3, and the x2 is 2/3 of alpha 2, and the x3 it's 2/5 of alpha 3. Okay, so we are able to find the unknown coefficient in terms of the known polynomials pt here. Okay. All right. So this shows that the P3 is in the span of B. Right. B here is just the set of all Legendre polynomials of degrees less than equal to 3. So this is here. And so this is implies that P3 is equal to the span of B. Right? So this is the first part. Now the second part is that B is linearly independent. Okay, so consider a linear relation on the B. Okay, so so we consider linear relation. To 0. Okay, and so when we, just like this situation, so when we plug into the Legendre polynomials, we find that we have x0 minus 1/2 x2 plus x1 minus 3/2 of x2t plus 3/2 of x2t square, 5/2 of x3t3 equal to 0. And then once again, this is the 0 polynomial. Okay, so this is a 0 polynomial. So by definition, all the coefficients should be 0. Okay, so this is equivalent to say that x is 0 Okay, and this is the same as here, that alpha 0 is 0, alpha 1 is 0, alpha 2 is 0, and alpha 3 is 0, right? It's just like the situation that we have 0, 0, 0, 0. So that this is a solution of x0, x1, x3, x2, x3, by using alpha 0, alpha 1, alpha 2, alpha 3. Okay, so but as we know from here, you may think about this is alpha 0. Alpha 0 is 0. Alpha 1 is 0. Alpha 2 is 0. Alpha 3 is 0. So that you get, because everything is 0, alpha zeros. So you see that x0 equal to x1 equal to x2 equal to x3. Okay. So that B is linearly independent. Okay, so the conclusion is that is a basis for P3. Questions? All right, so no question. Right, so you know the task to verify a set of vector in a vector space to be a basis for this vector space, right? You have to justify two things. All right, so the set of columns of an n times n invertible matrix is a basis for Rn over for Cn. Depends on the matrix has real entries or has complex entries. If the matrix has real entries, then its columns form a basis for Rn. But if the matrix is complex, then its columns form a basis for Cn. All right, so we let A be an n times n invertible matrix. Okay, and the column space COLA of A, it's just the AX for all X in Rn over Cn. Okay, so this is by theorem. (5.1.10). Okay, a very simple theorem we mentioned last Friday. So, okay, so the column space is this one, and also we know this is x1 a1 plus x2 okay. So exactly this is the column space is just the set of all linear combinations of columns of A. Okay, here. All right, so this is the case that now for each B in Rn or in Cn, we have x equal to A inverse B is also in Cn. Right? So because A is invertible, so that for each B in the Euclidean space, we have a vector in the Euclidean space by multiplying the B vector, right, with the inverse matrix of A from the left, say. Okay, so this is the case. So such that when you do the multiplication, so this is A, all right, so you get the B here. And the AX is in what? In the column space of A. Here, right? A multiplied with arbitrary vector in the n-dimensional Euclidean space is always in the column space of A. Yeah. Okay, so every vector in the Euclidean space is in the column space of A, right? So that the Rn over Cn will be in the span. Oh, sorry. It's in the column space of A here. Okay, so this implies that Rn or Cn is just equal to the column space of A. Okay, because the column space of A must be a subset of Rn or Cn. Okay, so they are equal. Okay, and so this is actually the span. By definition of the column space, we know this is just the A1, A2. Okay, so it's the span of the n columns of A already. All right, now so we show that, yep, this set of columns, the set of columns span the Euclidean space. So the only thing left is to show these n columns are linearly, these n columns form a linearly independent set. All right, so consider a linear relation okay on the set right. So this linear relation we write it as alpha 1 A1 plus alpha 2 A2 plus da 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 plus alpha n and equal to the zero vector. But this linear relation can be rewritten in the following way. We did that many times. Okay? And this is equal to A so this is the matrix equation, and so A is invertible, so that okay, so that means that this is indeed a zero vector, and so all the coefficients are zeros. So that means that alpha 1 all right, and so that A1, A2 up to AN is linearly independent. Okay, and we have done. So we have shown that the set of all columns of an immutable matrix span the Euclidean space, and this set of columns is a linearly independent set, so that is a basis. Okay, and we finish the proof. Questions? Sorry about that. Has been blocked by the table here. Okay, the next theorem is actually a theorem we have visited before in chapter 2. Okay, so we let B be a basis for a vector space. Then every vector V in the vector space has a unique representation, okay, as a linear combination of distinct vectors in the basis. Okay? Okay, and recall theorem 2.4.6. Okay, so I write the theorem we encountered before here. Let me write it down. So let S be a non-empty linearly independent subset of a vector space V, and each vector U in the span of S has a unique representation as a linear combination of distinct vectors in this. Okay? So in chapter 2, we prove the theorem here. So X is a non-empty, linearly independent subset of a vector space V. And each vector in the span of X, right, has a unique representation as a linear combination of the distinct vectors. Now, if the S is a basis for V, so now as stated in Theorem 5.2.2, if this is a basis here, if this is a basis, of course this basis is a non-empty linearly independent subset, of course. And because V is a basis of V, so the span, what? The span is equal to V itself. Okay? So it's V. So that says that each vector U in the vector space V has a unique representation as a linear combination of the distinct vector in B. Okay? And this is exactly Theorem 5.2.2. Okay, so Theorem 5.5.2 is a special case of Theorem 2.4.6. Okay, when the SSA is a basis. Okay, so I don't need to go through the proof of this theorem because we already done that in chapter 2 already. Questions? No? Good. All right. So we're back to all right, so now we consider a vector space. All right, so we consider a vector space V, which has a finite ordered or indexed, if you like to say, basis B U1, U2 up to UN. So suppose that we have a vector space. This vector space has a finite ordered basis B. So this basis consists of n basis vectors. Now, by theorem 5.2.2 there, each vector in the vector space can be expressed as okay, so we uniquely as here as a linear combination of vectors. They must be distinct, right? Because if the index set has equal vectors there, then this set must be linearly dependent, trivially, okay? So to be a linearly independent subset, index set, all the indexed vectors are distinct. All right, so we have this one, linear combinations, right? Uniquely means that the coefficients C1, C2, and Cn are unique. Okay. the column vector. So we use the coefficient. We define a column vector C1, C2 up to Cn, and define these column vectors by using the coefficients C1, C2, and Cn put together, all right, and name it as the bracket V sub basis B, so that this column vector is called the coordinate vector of V associated with the ordered basis B. Okay? We order the basis vector because we want to put into a column vector. Okay? So one by one, this is the first component, second component, etc. All right? So this one is called the coordinate vector of V associated with an order basis B here. So that this column vector is unique, all right, for each vector V. So before you talk about coordinate vector, you have to fix a basis first. Without a basis, you cannot talk about coordinate vector. Okay, so let B U1 be an ordered basis for a vector space V. Then the function T from V to the Euclidean space with is a bijective linear transformation. Okay, it's a bijective transformation. Right, so proof. So let X, Y be in V. So let X, Y be in the vector space, and alpha a scalar. Okay. Now, since B is a basis for V, they are unique scalars, C1, C2 up to Cn, and D1, D2 up to Dn, okay, such that x x is a linear combination of the basis vectors in B. Okay. Right, so we have that. And then when we add them together, okay, when we add them together, we combine the like terms. So we have and alpha x okay, right, so we have all these data there. Now we take coordinate vectors associated with basis B. So now T of x is equal to this coordinate vector, which is C1, C2 up to Cn. T of y is y, which is D1, D2, Dn. Okay? And T of x plus y, x plus y with a vector, which is C1 plus D1, C2 plus D2, Cn plus Dn. Okay, and T of alpha x with a vector. This is alpha C1, alpha C2, alpha Cn there. Okay, so from these data, we have the images of x, y, x plus y, and alpha times x. Okay, so we have all this information. So then we compute Tx plus y. This is equal to, and this is C1 plus D1, C2 plus D2, Cn plus Dn. All right. So this column vector is the sum of two column vector. Okay, and this is the coordinate vector of x plus the coordinate vector of y. So this is Tx, Ty. Okay, so we have this relation T of x plus y equal to Tx plus Ty. And T alpha x here, this is alpha C1, alpha C2, alpha Cn. So it's alpha C1, C2 up to Cn. Okay, so this is the properties of column vectors. And this is alpha x B, this is alpha T of x. Okay, so we have these two. And with that, so by theorem 2.4.c, T is a linear transformation from V to Rn over Cn. Okay? So now we establish that the coordinate vector, forming the coordinate vector is a linear transformation. Okay? Now we have to show that this linear transformation is bijective. So we have to show that it is untrue and one-to-one. Okay? So to show that it's untrue, we consider, so for a vector, C1, C2 up to Cn in the Euclidean space, right? So for a vector, this is in the codomain, right? So to show that this function is untrue, we have to show for each element in the codomain, there exists an element in the domain such that the element that we select in the codomain is the image of that element in the domain. Okay. All right. So for a vector in the codomain, we let V equal to C1 U1 plus UN, okay, which must be in V, right? So we use the column vectors in the Euclidean space, all right, to form a vector V in the vector space. All right, then we have TV. Now we want to check that this column vector is the image of the constructed vector V. Okay, so that TV here, and by definition, TV is just the coordinate vector associated the basis B. But from the expression in here, V is a linear combination of basis vectors U1, U2, UN in B. So of course this is indeed C1, C2 up to Cn. All right, so immediately we know this result. Okay, so which shows that T is onto. Okay, so every vector in the codomain, we can find a vector in the domain such that the image of this vector V is the selective vector C1, C2 of Cn. All right. To show that T is one-to-one, it is sufficient to show the kernel of T is trivial, because T is a linear transformation. Okay, so this is the if and only condition. All right, so we let X is a vector in the kernel of T. All right, So that means that T of x is 0 vector. Okay? And 0 vector is 0, 0. Okay? And this is the coordinate vector of x. Okay? So the coordinate vector of x is equal to the all 0 vectors. Alright, so this implies that x is 0 u1 plus 0 u2 plus plus 0 un. So this is 0 vector. Immediately, because that coordinate of x are zeros, so that x can be recovered by taking the linear combination of the basis vectors in B. All right, and so this is 0. So this implies that the kernel of T consists of the 0 vector only. Okay, and so T is 1 to 1, and we have done. Okay. Questions? Okay. Now I developed a couple of theorems needed in the further discussion. Okay, so a linear transformation is bijective if a nonlinear is invertible. And in this case, its inverse, okay, from W to V is also linear. Okay. The first part of the theorem has been proved before. Okay, so because that since T is a function itself, a linear transformation is just a special type of function. So T is a function from V to W. It is bijective if and only if it is invertible. By theorem 2.3.8. Okay, so we proved that before in chapter 2 for general function. Okay, all right. So the first part has been done before, right? So we have to check the second part. If a linear transformation is invertible, then its inverse must be also linear. It's also a linear transformation. Okay, so now for W and the W prime in the vector space W in the domain, okay, of the T inverse. So there exists V and the V prime in V such that TV is equal to W and TV prime is equal to W prime. Because T is onto, okay? T is bijective, so T is onto. So that for any vectors in the codomain, we can find vectors in the domain such that they are images. Okay, so you can find them. Okay, and then because invertible, so that the T inverse of W is equal to V, and T inverse of V of W prime is equal to V prime. Okay, because they are one-to-one and until. Okay, so the inverse of W is V inverse of the prime is V prime. Okay, so we have all this data is there. Okay, so now for scalars alpha and beta, so we have T inverse alpha W plus beta the prime. Okay, so we want to show the linearity of T inverse. Okay, now the W is TV, and the W prime is TV prime. Okay, so we just do the substitution. And now, because T is linear, right? T is linear, so we can combine this, okay, observe. Okay? Now, because T inverse is the inverse of T, so this is alpha V plus beta V prime. Okay? All right? And again, alpha, but V is T inverse W, and V prime is the inverse of W prime, and we have done. So this is exactly the linearity. Okay, so the T inverse of this linear combination is equal to the same linear combination with the same coefficient, but now replaced by their images, okay, under the T inverse. Okay, so now we now know the inverse is linear. Okay. Okay. All right. So okay, the second supplementary theorem say that the composition, so the composite X composite T of two linear transformation T from V to W and S from W to U is also linear. Okay, so the composite of two linear transformations is also linear, and the proof is quite straightforward. So I write it down quickly. So for V prime in the domain of T, and the scalar alpha beta, so we have that we test, okay, we test the image of this composite, all right, so that is X by definition right, of the composition is this one. And first of all, bilinearity, we have bilinearity of T, we have this one. Okay. And again, bilinearity of S, we have and by the definition of composite, okay, so we show that indeed this composite is linear, right? Okay, so I think I stop here. Any questions? Okay. No. All right. So just take a break and we start the quiz at 11:20.